please, Benny. Try, go ahead. You should be able to.
Okay. Is this okay?
Yes. Maybe if you share full screen, then we're gonna not see the. Well, yeah, I think it's good enough.
Okay. Good afternoon, everyone. I'm Benny Chin, a researcher from Singapore, and I'm currently working in Singapore University of Technology and Design, SUTD. This study was supported by an SUTD grant. Here I will be presenting a study that was done by Roland and I. Sorry?
Can you just stop a second? And I wanted to.
Okay, sure.
Okay, so very, very precise. We're all on time. We don't have that many people around yet. I hope there will be people around. So the idea is that it's going to be 4 talks by each with a slot of 15 minutes. I'm going to give you. I mean, in this case, I see the video is recorded, but I'm going to give you in general like the market 12 minutes, and then we have with the hope of having a few questions up. I think it's very nice today because we have a bunch of different approaches, so more theoretical and more applied works here. And so I wanted to introduce you, Benny, but you did it already, so please now go ahead and enjoy.
Okay, thanks. So let me start. I'm currently working in Singapore University of Technology and Design, SUTD. This study was supported by an SUTD grant. Here I will be presenting a study that was done by Roland and I. The title is The Identification of Super Spreaders and Super Susceptibles Locations from Directed and Weighted Human Movement Networks for Disease Control and Prevention. The identification of super spreaders or the most influential nodes is a typical and frequently discussed topic in complex network research. So what we are presenting in this talk is about the application of using the most influential nodes concept on the human movement network, which is a directed and weighted flow network, and we discuss this topic in the disease spreading context. First of all, what is super spreader? In a disease spreading process, there are some people who are responsible for most of the spreading events. Previous studies observed that about 20% of the people are responsible for approximately 80% spread of an infectious disease. The 20% are the super spreaders. For example, the figure on the right is the infection chain that was mapped on February 13 about how the COVID-19 spread to people who are coming from different places like Singapore, South Korea, UK, and Malaysia in a hotel in Singapore, and which is then spread to France and UK by the person highlighted with the red box, who can be considered as a super spreader in this infection chain. And another super spreader is the Malaysian in the blue box, who also triggered the first local transmission cases in Malaysia. However, it is very difficult to trace the infection chain for a large outbreak and a highly contagious disease such as COVID-19, because it is quite impossible to get the physical contact network for everyone in a city or everyone who is infected. Therefore, we bring this concept from the interperson level to another scale level. The spatial network within a city, that nodes are places and edges are the flow between places. Previous studies highlighted that there are 2 main features for becoming a super spreader. First, it has a lot of brand, that is strong local intensity, and second, it's friends located in different communities, that is high semi-local diversity. Having a large number of friends indicating that he or she can spread the objects or disease to a lot of people or target. The diversity of friends indicated the spread ability to different groups or locations in the network. If all friends were in the same group, then this will restrict the spreading process to a small subset of the network. So the diversity of friends need to be high in order to become a super spreader. Next, what is special in spatial flow networks that we need to consider and incorporate into the spatial superspreader analysis? Many superspreaders analysis focus on finding the most influential nodes in a friendship network, which is an undirected and non-weighted network. In a flow network, nodes can be an origin or a destination of every directed edges. If we apply the concept of superspreaders or the most influential node to a directed network, then we are probably talking about the power to spread something, that is the most influential origin. How about the destination? Using the same concept but with a different perspective, there's another type of nodes, the most influenceable destination or the most easily get affected destination. We call this type of nodes the super-susceptibles location. Both concepts, the super spreaders and super susceptibles, are important in the context of disease spreading. Based on the key feature of super spreaders, that is the local strength, and the semi-local diversity, we converted these concepts into three parts of the measurement. First is the strength of incoming flow or outgoing flow. A super spreader should have a large amount of outgoing flow, and similarly, a super susceptible should have a large amount of incoming flow. Second, the zone diversity of incoming or outgoing neighbors. A super spreader's outgoing neighbors should be scattered at different communities or having a high zone entropy, whereas a super susceptible's incoming neighbors should be coming from different communities. Third, the corners diversity of incoming or outgoing neighbors. The outgoing neighbors of a super spreader should be going to both cores and peripheries of a network, whereas the incoming neighbors of super susceptibles should be coming from both cores and periphery. In these figures, the conditions in the blue boxes were used to calculate the susceptible index or SUI, and the conditions in the red boxes were used for the calculation of spreader index or SPI. This study used the Republic of Singapore as study area, and this is the residential population that's been mapped. We use subzones as the analysis unit in this study. We use the public transport data, including the origin-destination flow of buses and trains, for the construction of the flow network. In Singapore, more than 60% of working adults and students use public transportation for their daily commute. This figure shows the train and bus ridership from last year, November to June of this year. Because the data starting from February may be affected by various unknown factors, we use only the stable data from November to January to perform the analysis in this study. These are the first intermediate results showing the distribution of the strength of flow. In this study, we used the in degree, weighted in degree, out degree, and weighted out degree to capture the strength of flows into and leaving from each subflow. The four maps at above show the 4-degree spatial distribution for weekdays, and the two maps below show the differences between weekdays and weekends for the weighted degrees, which indicated that they are somewhat similar between weekdays and weekends. This is the second intermediate results showing the distribution of the network communities that is defined as zone in this study. We use map equation to detect the zone from the two human movement flow networks. The zones on above is derived from the weekday flow networks, and the bottom map show the zones for the weekends flow network. Map equation was used instead of modularity-based method is because map equation attempts to keep larger flow within the communities, and this is more suitable for our use case. These intermediate results show the distribution of the corners. We use weighted K-shell decomposition to calculate the corners level, then use the median of corners distribution as cutoff to categorize the subzones into either core or periphery. Because it is a directed network, so using the in or out degree in the calculation, we can get the in corners or out corners. For the zones and corners result, what we need is the diversity of their incoming or outgoing neighbors. So we calculated the two normalized entropy equations to get the zones and corners entropies using their incoming and outgoing neighbors zone or corners categories. This map shows the three parts for calculating spreader or susceptible indexes, including the strength of flows in the left column, zone entropy in the middle column, corners entropy in the right column. Each row is used for the calculation of SPI or SUI for weekdays or weekends. And we use geometric average of the three parts, the strength of flows, zone entropy, and corners entropy for calculating SPI and SUI. So this is the first main result. We have the frequency distribution of the SPI for weekdays and weekends on top, and the SUI for weekdays and weekends on bottom. We use the IQR approach to identify the upper outliers. These are the super spreaders or SSP, the super susceptibles or SSS. For those below the IQR and above the Q3, we call them the secondary spreaders or secondary susceptibles. The two maps on top are the super spreaders for weekdays on the left and weekends on the right. The two bottom maps are the super-susceptibles for weekdays and weekends. The subzones in dark red are the super-spreaders or super-susceptibles locations, and the pink subzones are the secondary spreaders or susceptibles locations. One key observation we can get from this map is that most of the super-spreaders or super-susceptibles located at the local hubs within a region. And most of the subzones in the central business district, which is the central region here, are not the super spreaders or super susceptibles. A lot of them are secondary spreaders or susceptibles. Some of the small subzones, for example, H, the Woodlands Region Center, and B, the Jurong Gateway, are the super spreaders and super susceptibles locations. These areas contain a low number of residential population, but the two subzones contain the main bus and train interchanges. So these are the typical hub locations within a region. Most of the super spreaders are also super susceptibles. Only a small number of exceptions exist. The main contribution of this study is in two folds. First, previous complex network studies on super spreaders focus on the identification of the most influential nodes within an unweighted and undirected network. Here we presented an analysis framework focused on the spreadability in human movement networks, which is a flow network that the direction and intensity of flow should not be neglected. So our first contribution is that we presented a framework to identify super spreaders, which is the most influential nodes, and the super susceptibles, which is the most easily get affected nodes in a weighted and directed flow network. Secondly, the identification of super spreaders persons is to find the key person and trace the chain of infection. However, this is difficult for a highly infectious disease such as COVID-19 because the data for physical contact network of everyone in a city is quite impossible to get due to the scale and the privacy issue. The study we have presented is different from previous studies that we used another view, which is the population flow patterns that indicates the potential spread of disease. In simple words, what we have found is that which area is more dangerous than others. The result is about subzones, not about persons. So this could be useful for some intervention policy making, for example, the lockdown of super spreader locations, or provide more monitoring resources at the super susceptible locations. Here are the three future plans that we think we can do to continue this work. First, the comparison between different cities, for example, Tokyo, Hong Kong, Taipei City, and so on. The public transports are also the main transportation in these cities. Second, the analysis about the super spreaders and super susceptibles in a larger scales like the regional or global scales. For example, the global flight network and the global bilateral migration network. Third, we can use the super spreaders and super susceptibles in different extent. For example, the spread of information in social media. Okay, this is the last page. Most of the materials in these slides is extracted from our published work on scientific report, spatial super spreader and super susceptible in human movement network. That's all. Thank you.
Good afternoon, everyone.
Okay, thank you very much. This was very interesting. So I'd like to ask the people in the audience whether anybody has questions. And if you do have questions, I mean, either just let me know somehow and I'll give you the word, or write them down in the chat, please. For the moment, I don't see anything. So I have one myself, and I was wondering, so actually it's two questions. So the first one is whether, there's been a lot of talk online in terms of of the tension between saying, well, there are some locations or some people who are super spreaders or very susceptible, versus the temporal version of that, which is, some events actually are super spreading. And I was wondering whether you thought about these and whether some of the technology that you developed here could actually be leveraged for that in terms of, say, temporal graphs and so
on. Sorry, are you talking about the super spreader events and something like that?
Yes, because right here, so my understanding is that you are able to basically decide whether spatially you have different locations that are giving you different sort of chances of being a super spreading event. And I was wondering how much of these could actually be sort of leverage to, instead of thinking of like sort of static super spreading patterns, but rather, or super susceptible patterns in terms of the temporal part of this, where we can actually pick this up, for example, from events and flow data and that kind of stuff.
Okay. Yeah. So actually, we have also tried to analyze the super spreader and super susceptibles in different, I mean, in different months, the flows network from different months. And what we have found is that usually the result is quite robust. And so I think the results, because I think maybe it's because the population flows patterns is quite similar in the proportion of the flows is similar as before, although it's dropped very significantly. And yeah, so I think that's all.
And then, so if there are any questions people ask me, let me know. And then the other thing is whether you thought and whether there is data that you can use to try and sort of verify these on in terms of epidemic incidents in the different neighborhoods and so on, and see whether it actually corresponds.
Yeah, actually we are also thinking about to verify the results, but in Singapore I don't think we can get the data because of the privacy issues, and the government, they don't want us to get the data. And second, because what we have been analyzing is the potential to get infected or to spread the disease. And what the data we are using is also from last November to January. So it's not the data exactly for the COVID-19 periods. So I think we cannot just compare them like, yeah.
I see. Okay. Thank you very much.
Okay.
We don't have any other questions, so we're really running a couple of minutes late in perfect Italian fashion. So I'd ask Guilherme, is the second speaker? Yeah, Guilherme Ferraz de Arruda to switch on and maybe start sharing his screen. So Guilherme is a postdoc at ISI Foundation, and well, I think you can introduce yourself and go on from there, please.
Just a second. Okay. Oh, can you all see the screen?
Yes.
Okay. Let me...
But it's not started, yeah, or there is no sound.
Ah, there's no sound. Okay.
Probably you have to put in the sound from Zoom. You have to say that you're sharing a video.
Okay, I must have forgot. Okay, just okay, now.
The best. First of all, I would like to thank everyone interested in our research and watching this presentation. I'm Guilherme, and I will present our work on social contagion models on hypergraphs. So, when I was preparing this presentation, I'd like to bring a slide of motivation that could appeal to everyone. The best I could find is this meme here. Here, the idea is to emphasize that communication through groups, in this case WhatsApp groups, are intrinsically different from the one-to-one communications. So, in this presentation, first I will present a bit of the literature context motivating our model. Then I will define hypergraphs, which are the main mathematical object here, comparing it with a graph. Next, I will introduce our model for arbitrary hypergraphs. And after that, I will focus our analysis on analytically treatable cases, which will show the different types of behaviors we can observe. I will conclude our results with Monte Carlo simulations in more general structures. Finally, I will end this presentation by connecting our model with the first section literature results. Okay, first of all, the motivations. Our work's initial motivation was this paper published in Nature Communications, where the authors considered simplicial complexes to model social contagion. In this model, they assumed that higher order structure would imply an extra spreading force. As a result, they observed discontinuities, which contrast with the traditional spreading models in networks. Although their model represents a significant advance, they are still limited to simplicial complexes. Here, in our model, we will relax this constraint by considering hypergraphs. Also, another important motivation for our work is this paper about tipping points in social conventions. Here, the researchers found experimental evidence of critical mass dynamics in their experiments. In words, there is a critical group size that can overturn the established behavior. This critical mass dynamics will play a central role in our model. So, first of all, we define the hypergraphs. Hypergraphs are composed of two sets, a set of nodes and a set of hyperedges, while the second are subsets of nodes with arbitrary number of elements, which are nodes. The number of elements in each hyperedge is called cardinality. Note that if the maximum cardinality of a hypergraph is 2, then what we have is a simple graph. Okay, in short, our dynamics can be described as follows. To each node, we associate a Bernoulli random variable, which is 1 if the node is active and 0 otherwise. On top of that, we associate a collection of independent Poisson processes that will guide our dynamics. We associate a Poisson process with parameter delta, modeling the deactivation process for each active node. This is similar to an SIS process. For each hyperedge, we define a critical mass dynamics. If the number of active nodes inside this hyperedge is larger than an arbitrary and given threshold, we associate a Poisson process with parameter lambda that will activate all the nodes that are inside this hyperedge. With this prescription, we can write the exact equations that drives our dynamics, and this is written in the center of this slide. Unfortunately, this equation cannot be numerically solved. So, with this in mind, we follow the first order approximation, which is given by the equation in the bottom. Interestingly, to calculate the probability of the critical mass dynamics being active, we have to calculate all microstates probability. However, computationally speaking, merely multiplying the probabilities and summing them is not numerically stable. Note that we are multiplying very small numbers. Fortunately, we can overcome this problem by using the discrete Fourier transform. Okay, now we have the mathematical formulation of our model. We will begin our analysis with the simplest analytical case possible. Here we focus on the hyperblot, which is a random regular network with a hyperedge containing all the nodes. So, due to the symmetries of this structure, we can describe our dynamics with a single equation. This equation has two possible solutions, which we call lower and upper solutions, and are shown in this slide. Note that the lower solution is basically an SIS model in a random regular graph, which presents a second-order phase transition or a continuous phase transition. We can also move from one solution to the other by increasing lambda, thus this will imply in a discontinuity. This discontinuity here also allows us to interpret the jump length as the latent heat in thermodynamics. In other words, we have some energy that is absorbed or released all at once. In this specific case, they can be analytically obtained as well as the tipping points, and which are shown in this slide. In summary, from the analysis of this simple case, we managed to find second-order phase transition, discontinuities, and hysteresis. I also would like to remark that if we consider I star instead of the random regular network, the second-order phase transition will go to 0 in the thermodynamic limit, slightly changing the parameter spacing, especially in panel B. Also, This type of model allows for something that is similar to a Carnot cycle in a social context, maybe providing an additional hypothesis to changes in social norm. Moreover, in the paper, we proved the solution's stability and showed a more in-depth analysis of these structures. So, if you are interested, I would like to refer the view to the paper. Okay, so far we focus on the hyperblob because it's analytically treatable, and with this analysis we can have a better idea about the types of behavior that are in our model. However, we know that real structures are more complex. Thus, we evaluate hypergraphs with exponential distribution of cardinalities, aiming for something closer to reality. In this case, we focus on only on Monte Carlo simulations. In the top left panel, we present the susceptibility, which presents a peak in the critical point in a second order phase transition. Complementary, in the bottom left, we show the order parameter, which is the number of active nodes. Here, we can see that we only observe discontinuities, and we don't observe any of the second order phase transitions, and the discontinuities are observable both in the order parameter and the susceptibility, as expected. Also, in the right panels, we can see the microstates distributions for the upper and lower solutions for a given set of parameters, here for theta equals to 0.2. Here we can observe that the upper solution is characterized by a bell-shaped distribution, while the lower solution presents a decay with a peak near the absorbing states. With that, I conclude our results. So, our initial motivation for this model was the experimental evidence of a tipping point in social context. In this context, there is an apparent contradiction. Some works report that the critical mass levels needed to change the equilibrium is around 10%, while other works report that these levels are around 30 to 40%. Our model offers two possible explanations. The studies reporting levels around 30 and 40% can be modeled as single groups, while the critical mass of 10% corresponds to the whole population. Thus, in this case, our model accommodates both concepts due to the hyper-edge intersection. The second possible explanation is that we have B-stability. So, we can have that both levels are possible, and we just sample from the upper or lower solutions. And finally, to conclude, I'd like to mention that hypergraphs impose virtually no constraint, thus being the ideal mathematical object in the social contexts. Our model presents a vast parameter space covering different types of behavior. Moreover, if that's the case, the standard model might not be enough to describe real phenomena. And finally, I'd like to motivate further research on higher order social models and hypergraphs. So, thank you. If you're interested, I would like to refer to our paper. And again, thank you.
Thank you, Guilherme. This was very clear, very nice. Do we have questions for Guilherme on this? As you can imagine, I've got a bit of a conflict of interest in asking questions myself. Because if there are none, then I would actually ask you, Guilherme, to talk about some. Oh, yes. Can you explain a bit on the Carnot cycle idea and how memory would work, please?
Okay. How memory would work? I'm not sure if I can answer this because we didn't consider memory at all. We are using a Markovian process. I know we might have some guesses from the literature, but from our model itself, we cannot. The idea of the Carnot cycle is that we have just two possible solutions, a lower and upper branch. And then if you move from one branch to the other, you cannot go back directly. You have to follow the branch and then go back. So the idea here and the hypothesis maybe is that in some kind of social contexts, like I like to think about left and right in politics or these kind of things, but this is just informal argument. You have to move through these left and right phases to, you cannot shift them right away. You have to move in this cycle, and this would be this would provide for social scientists a different type of explanation, a different mechanism. It would be something like how group dynamics is actually playing a role on this. But this is a very open question. It's something that we would love to hear from social scientists and data scientists to prove or disprove our hypothesis. I don't know if I answered the question or not. Please ask me again. And also on Wednesday, I'm going to present some other results from this work on the Mixed Next satellite. So if you're interested, please join us.
Okay, yes, I was going to ask something about that next work, which I'm not involved in, but since you have the talk there, then I refer everybody to that talk over there. And so let's thank Guilherme again. I'll just clap your virtual hands, please. Right now, so I'll move on to the next speaker, who's Manlio de Domenico from FBK Foundation. He's actually not here because of a little sort of mess up with the time zones. So he gave me his video, and now I'll try to see whether I can share that appropriately. But luckily we do have a collaborator of Manlio here. Manlio is here, so in case you want to ask questions, then he'll be able to help you with that at the end of the talk.
Hello, everyone.
I'm not in the paper.
Thanks for giving me the opportunity to give this talk today. This is a work about epidemic spreading, but it's not about COVID-19, and it's done in collaboration with two other labs at Fondazione Bruno Kessler. So the real-world systems consist of interconnected units. This is true at the molecular level and also at the level of our society. And in the last decade, it became very important, one more ingredient to better account for this level of, for the level of complexity that is encoded into this type of systems. And this is multidimensionality. So what is we use multi-layer systems, multi-layer networks as a proxy to describe a broad range of empirical systems. Here there is a multi-scale representation of the system going from the molecular level up to the population level, where you have multiple layers because, for instance, you want to encode social ties, family ties, job ties, and so on. And in these layers, behavior and information, as well as disease, spread mostly. So these are the layers that we are interested into. And there is also another paradigm for using multi-layer networks in order to describe, for instance, human mobility at different scales, from the urban scale here within a city up to long-range intercontinental transportation networks. And another factor which is very relevant for multi-layer network modeling is the fact that you can model different types of dynamics on the top of these networks. On the one hand, you have single dynamics, like for instance a random walk or a diffusion process that spread through the layers of the system. But on the other hand, you can have coupled dynamics, where in each layer you have a distinct dynamic. And in the last decade, it became very important, one more ingredient to better account for this level of, for the level of complexity that is this type of systems, and this is multidimensionality. So what is this? This is related to the multi-layer feature of many empirical systems, which consist of separate layers, where each layer is encoded by a color here, and in each layer the units exhibits different types of interactions. We use multi-layer systems, multi-layer networks as a proxy to describe a broad range of empirical systems. Here there is a multi-scalar representation of the system going from the molecular level up to the population level, where you have multiple layers because for instance, you want to encode social ties, family ties, job ties, and so on. And in these layers, behavior and information, as well as disease, spread mostly. So these are the layers that we are interested into. And there is also another paradigm for using multi-layer networks in order to describe, for instance, human mobility at different scales, from the urban scale here within a city up to long-range intercontinental transportation networks. And another factor which is very relevant for multi-layer network modeling is the fact that you can model different types of dynamics on the top of these networks. So on the one hand, you have single dynamics, like for instance a random walk or a diffusion process that spread through the layers of the system. But on the other hand, you can have coupled dynamics, where in each layer you have a distinct dynamical process. In this case, you have a broader and richer spectrum of phenomena that can happen with respect to the first case. And actually, the second one is the framework for the work that I am going to introduce and to discuss today, where we will be using the multi-layer representation in order to integrate the different types of population dynamics. Let's start from the type of data that we use. Here we use phone calls, and specifically we use call detail records, which in the last decade have been proven to be really effective in encoding human flows and human mobility between different spatial patches, geographic areas. And there are a lot of papers now making use of this type of data in order to gain new insights about human behavior, but also to human behavior coupled with epidemic spreading and other types of dynamical processes. How? This is mostly done by mapping the calls or the behavior, how the behavioral usage of your phone into detailed records, and those records are then mapped into the antennas or the areas where the antennas belong to. And in this way, you can coarse grain essentially the path of your trajectory into a coarse-grained representation for this trajectory. And while you do that, of course, in an anonymized way, aggregating all the anonymous information into flows at the level of a population moving between adjacent areas, like here, you can start modeling or design models in order to account for this type of data. And in the last years, I have been involved mostly in models coupling a layer where you have human mobility, so where you have the flows, so you can extract the flows from this type of information, with a layer where there is human communication, using again the same type of data. And then you can use or encode epidemic spreading by means of force of infection models or reaction diffusion models, according to what is more convenient for the problem at hand. But essentially here is the major breakthrough where you can encode each dynamical phenomenon into a distinct layer. Going straight to the data that we used, here we participated to an international data challenge proposed by Turk Telecom, and providing the data about so more than 40 million total conversations for a total of more than 20 billion minutes concerning the duration of talks concerning population in Turkey. Two types of population. The first is the local host, the Turkish citizens, and the other type is Syrian refugees. We have data for a total of 1 million people, more or less, and more than 900,000 are related to Turkish individuals, and the remaining are related to refugees. And we have participated also, we won the data challenge for in the public health track. And you can find all the details of what I'm going to talk about in our very recent publication. So let's start from the parameter of the epidemic model. So we focus our attention on measles. And we obtained the parameters for the epidemic spreading by fitting real data observation obtained from WHO data. Here you see the reported number of cases in Syria, and we use it in the ones in red are the ones used to fit the exponential growth of the disease in order to get the parameters. And this is the percentage of cases stratified by the age of the population. Here you see, this is an interesting point, as we'll see in a while, the percentage of immune individuals in Syria stratified by age. And as you can see here, the youngest ones are the one with less immunization level. While in this plot here we show the percentage or the fraction of individuals living also from the population of Syria and the one related to refugees, Syrian refugees living in Turkey. And I want to focus your attention on these two plots because for an R0 basic reproduction number between 12 and 18, that is the one typical for measles, you need an herd immunity between 91 and 95%. And here you don't reach those numbers for the youngest cohort of the population. That is also the one, the majority of the population of refugees in Turkey. Then there is this public health problem related to the fact that Syrian refugees might be responsible for potential outbreaks of measles in Turkey. We have tried to estimate this type of risk, and we have found that areas with more than 5 or 8% of susceptible individuals are the ones potentially at risk for sustained local transmissions, and they are mostly located along the borders with Syria and in Istanbul, for instance. And this corresponds to more than 2 million people between Turkish and Syrian refugees. So the point is, can we tune social integration in order to effectively reduce the risk of a measles outbreak? To this aim, we designed a dedicated model where we have a network of patches. Each patch is the distinct district of Turkey. And in each district, in each patch, we have our multi-layer model where we have essentially two distinct populations encoded by each layer. One is for the Turkish citizens and the other one is for the Syrian refugees. And then the interactions between those two layers accounts for what we call social integration. So the interdependency between those two layers is mapped into a parameter which encodes social integration, so the mixing of the population. And those two populations are distributed when these numbers are encoded with these numbers, and each population moves according to a specific human mobility model, which is encoded by this matrix, which is obtained from the observation from the data. The contact rates are different for the two populations. We have type 1 and type 2, encoding how differently they move and interact with the other group, as encoded by the parameter alpha. And then we have population-dependent transmission rates, betas, here, which enter into the definition of the force of infection that I mentioned at the very beginning of the talk. So you see here that we have two distinct forces of infection, accounting for the different ways in which the two populations move and spread through the network, and for the integration, the social integration parameter. Our model is an SIR model with the two populations, which are coupled together according by means of the two forces of infection, so as I have shown in the previous slide. Going to the results, and towards the end of the talk, we see that for a worst-case scenario, where we use an R0 of 18 and we have almost at 12% of susceptible refugees, we have run many simulations considering the cumulative number of infections in two scenarios. In the top scenario, so here for these plots, we consider the distribution of refugees according to the ones that we observe from the data. In the bottom one, we redistribute instead the refugees according to proportionally to the local Turkish populations. And as you can see, in both cases, when we increase the fraction of contact, so the alpha parameter from 0 to 1, we see a decreasing number of infections. And between the two cases, this one is even better than the first one. So when we dispersed the refugees in a way that is proportional to the local Turkish population, the final incidence of the measles outbreak is lower than the current way, let's say, in which the Syrians are dispersed. So essentially, social segregation does not hamper, but rather boost the potential measles outbreak. This was somehow counterintuitive. But in some sense, we see that the way it works is a kind of effective herd immunization due to the Turkish population. So we have used multi-layer modeling in order to model coexisting populations. And the first countermeasure that we see from modeling is that we have to disperse local, proportionally to the local population. It is the one with a higher immunization level. And as a second countermeasure, we see that higher level of social mixing is beneficial. And as a third countermeasure, we have to prioritize vaccination campaigns of Syrians on the national borders because they are mostly distributed over there. And then let me say that CDR data, even if it's not perfect, it can be really reliably used to identify the potential spatiotemporal spread of an epidemic. So just let me say that if you want to know more about multi-layer models and analysis, there will be a dedicated satellite in 2 days from now. And I thank my co-authors and all of you for the attention. Here you can see the list of related publications. So thank you very much for the attention.
Okay, so apologies for the little mishaps earlier. Turns out that for future chairs, turns out that you cannot do something else while you're streaming a Zoom video because otherwise it stops. Unfortunately, I would love to ask you for questions, but the best I could do would be to sort of pass it over to Manlio. So I think you can do it on your own. And so I'd like to go on to the next speaker, who is Malbor Asllani. And he's going to talk about, wait a second, what was that? What is it? Yes, inferring the role of contact networks in population spreading models. I didn't understand whether you are in Limerick or in Namur from your double affiliation, but I guess yes. Both. So please share and go ahead.
So, okay, thank you very much, Giovanni, for this introduction. So actually, let me share first. Okay, is that okay?
Yes, works.
I hope this. Okay, perfect. So I have this double affiliation in the sense I'm a chargé de recherche in Belgium, on leave actually, because I'm in Limerick from a couple of years now. And I'm moving in a couple of weeks. But so my talk will be about, as you can see, we have tried to uniformize a little bit the two aspects, that main aspects that people model in general, related to contact networks, regarding, of course, spreading phenomena, not simply actually epidemics, and also that of meta populations, right? We found actually that strangely there is a gap in between, and what we have done here. Well, actually, this is joint work. There are several authors there. It was a part of the master thesis of Cédric Simal. Unfortunately, I don't have a picture of him here. From University of Namur, he did his Erasmus stage with us. In Namur, he was co-supervised by Timoteo Carletti, and he worked jointly with Bram Siebert here in Limerick. Bram is a PhD student, and of course, the head of our group, James Gleeson. Well, I know that you have seen these models, especially this last year, like everywhere, even in your dreams. But I'm, let's say, obliged somehow to shortly revisit, go through them. So here I have perhaps one of the main and most popular model, SIR model, as introduced by in the 30s by Kermack and McKendrick. Is a general model of three species, as we would use to say in mathematical biology, for instance. So we have the susceptibles, the infected, and the recovered individuals. We have two main parameters, the one of contagion, beta, and then of recovery, mu, that you can see here. And of course, referring to the famous law of mass action, proportionally to the concentration of these individuals, of these species, we can write down a set of differential equations, so we can see the evolution and of the system and so on. However, with the development of network theory in these last 20 years, people have moved on at looking at the social networks. So how indeed a given phenomenon, I mean, not simply an epidemics, can spread through a social network, a network of contacts of individuals. And now, if we have two individuals, I and J, we have that if I, for instance, is infected and is in touch with the individual J, which is susceptible, then with some probability, beta, the infection can occur. So at the end, both of them will be infected. Nevertheless, and this is, for instance, one famous model, a mean field model, because indeed, if we look the problem from the microscopic point of view, we have to write down a master equation in order to recover then this mean field equation. So in this case, we are using the individual-based mean field model. It is quite famous, it works pretty well. When you can see now that it is a modification of the previous model from the 30s, the original SIR1, and now you have the role of the adjacency matrix, right? So it is included in the equations. But we should think that if we are in a larger, let's say, spatial dimension, so if we will take into account the whole island, for instance, we have to take into account all the counties, or if we look even at a town like Limerick, we have to take into account the households, the schools, and so on. So in this case, we don't use anymore the nodes, but we use the metanodes, as it is, for instance, taken from the famous, this picture is taken from the famous review of Pastor Satoras and others. And indeed, inside a meta node, what we have is that we have the individuals, and again, they will interact somehow. We know that they will not be under the same conditions of well-mixed, like it was previously considered by the law of mass action, right? It is some kind of social interaction through some social networks inside. And indeed, we don't have anymore the same contagion parameter beta, but it is modified. It is this beta tilde that I'm denoting here. So it is the same for the reactions as you have seen at the original model of Kermack-McKendrick. The only thing that we are adding here is the diffusion between the metanodes. It is this network Laplacian definition here. And the main point is that we have now a modified contagion parameter. So it's not the one that you can measure in the lab where you put two people together, one infected, another one susceptible, and you have just to wait some interval of time to see for the infection. It is a contagion parameter, this one, that is measured statistically. So we have a given meta-population network and we derive it from the data, right? So what we aim here indeed is to take into account all these metanodes. That will be some local contact networks. They can be, for instance, households, as you can see here, blue, gray, and so on. We have children, they go at the same school. We have grown-ups, they will go at the same working place, and so on. And we want to infer actually what is this kind of contagion parameter that we derive usually from the data, right? And what we do is to rewrite the meta population where we put exactly the social networks, supposedly that we know exactly these social networks. I mean, the social networks will change in time and so on, but let's suppose that there will be fixed networks. And we take into account that the metanodes will have some social networks, contact networks inside. Now, the main difference with the models explained so far is that we have, for instance, a susceptible which is blue and is at some node at a given moment. The problem is that it cannot be like everywhere, right? So it is diffusing, but at a given instant of time, it is at one of these social networks, so not everywhere. And then this property will translate even in equations. And the same for the other individuals. So you can see blue, for instance, is susceptible, red is infected, and white is an empty space. So each individual has in the metanodes that it will visit, in this case, we are supposing it will visiting all the metanodes, will have some fixed position there in that social network. So, or it is or not on that metanode, and it is susceptible, infected, or recovered when it is at that given metanode. So in this sense, what we'll have is that we have, again, the same reaction diffusion model like before. The only difference is that now we take into account these social networks through some function, general function for the mean field model that you can see here. And we have used a notation. I mean, there are a lot of notations, can be called even a multi-layer if you want. But we are using a notation that we found it a bit more suitable to our way of thinking, is that of metaplex. It was recently introduced, and here you can have the reference from Ernesto Estrada. The idea is it is a metapopulation complex network. So it is complex in the sense that it has some, I mean, it can be seen even like a network of networks if you want, but it has some different kind of dynamics. So if, let's say, at global scale, we have the diffusion, at the local scale, we have another kind of dynamic, that of contagion. So this is the idea. And the main point is that if we sum the susceptible, infected, and the recovered individuals, fixing the index for the node inside the metanode and the index of the metanode itself, it doesn't sum at one, as I said to you before. We have to sum over all the metanodes. So a given individual, of course, it will be susceptible, infected, or recovered, but it will be at some metanode, right, in not all of them. And indeed, in order to write, for instance, using the individual-based model, it can be written this way. The first equation, I mean, the same will be, but this is the term that will repeat, right? It will repeat for the infected ones with a plus sign in front of everything. And for the recovered one, we don't have nothing. I mean, it's not affected by the local topology. And we can go with some very basic linearization around an equilibrium point for the three species. And also the other expansion is done for the average degree for a given meta node gamma. And what it can be recovered as somehow expected, but then I will show you the robustness of this method, that the new beta tilde that is adapted in general for the metapopulation model depends by the beta, the one that you can measure in a lab, for instance, depends by the density of the edges. So depends by the average degree, like the one shown here. And indeed, in order to see the robustness, using only the first order, so this is for the first order, we are taking here like local networks, scale-free networks. I thought that it wouldn't work that good. For instance, you can see the dashed curve is the curve for obtained by the averaging with a lot of independent stochastic simulations. And then you have the metaplex, the model that I showed to you, using the individual-based mean field model, is again the orange curve. Of course, we expect that if we have a perfect knowledge of the social networks, they will work quite good. But it works good even our approximation with a degree is the violet curve here. And then we used other attempts. So this is for the SI model, for instance, the infection versus time. We use even the clustering coefficient or the closeness. We hope that with the closeness, we can get some better insight, the peculiarities of the network and so on. But apparently they don't work at all compared to these other measures. And as you can see, it is the same for an SIR model, SIS, and so on. And in order to verify the peculiarities of the topology, the experiment that we have done is to take a ring. Of course, we expect that in a ring, you can see here for an SI model, the mean field approximation is the worst that it can occur for a lattice, for spatial networks in general. But with a very slightly randomization, so we are transforming through the Watt-Strogas technique, transforming the ring to some network with some links, it goes quite well to our approximation. So it is still quite robust and I mean quite intuitive actually outcome that of the degree, but not to capture even for topologies like scale-free networks and so on. You can see even for star, for instance, is the pathological case, for instance, of a single hub that you can see and only leaves. Even in this case, it works pretty well. And of course, it fails, for instance, for lattices. And that's all. So thank you very much.
Okay, thank you very much. Do we have questions from the audience regarding this?
Okay.
No, we don't. Well, what people think about that? I actually, so there is something I didn't understand, and probably because I got distracted at some point. So the results that you were showing at the end, I mean, all the curves that you're showing, I mean, they were all analytical, or you had like which ones were simulations, or they're all analytical results? How does it work?
Well, let me go once more. So we have the dashed curve is from the stochastic simulations. So you have the master equation, you simulate it through the Gillespie. Okay. Usually the notation is the dash curve is the ground truth, right? And the solid ones are from the theory. Now the theory is that the metaplex, if you have the full description of the social networks, of course, I mean that's the best one. The problem is they don't have that in general. You can have some, for instance, children. They are known to be quite dense in their social networks, whatever. So we have that. We take the degree, and the degree is for the violet curve. And then you have other measures here. So these are the main, let's say, comparison. And it works. It captures the behavior not bad, let's say, in general.
I see. And do you think you can actually add, for example, I mean, of course, it's very hard to have the full or approximate the full detail, the full information, but would it be possible to try and sort of guess what your IBMF would be, for example, if you had like age distributions, you know, in terms of which of the composition of your population? So I'm trying to think, you know, if you could relate something of this type to, say, for example, you know, the previous talk where the age distribution was very important.
Yeah, actually at the second order in the calculations because one expansion is done for the average degree, so the rest will indicate actually how broad, let's say, your distribution is the one that gives some insight on that. Not perfect, but of course it gives some insight. Here it is drawn only for the first order these curves, but one can get some insight in this sense.
Okay, thank you. So if we don't have any other brave question asker, I would like to thank again all the speakers and the audience in this session. I think this was the last talk for today, at least for me. So thank you very much, and bye everybody. Put your hands together virtually. At least, you know, we're gonna have the energy of that, and bye.